welcome to another edition of the Foundation Seminar. Today we have Dan Kapec. Pleasure to have invited on the black hole photon ring, old and new. It's from the CMSA, just downstairs. Welcome, Dan.
Okay, thanks first of all for inviting me to speak here. I'm going to discuss a couple of topics related to classical and quantum physics of the black hole photon ring. I realize that there are several experts in the audience, many of whom have written or co-written papers on the black hole photon ring. So some of this will be old hat to you, but I wanted to try to keep things more accessible to everybody. So just bear with me for the first half of the talk. So just to kind of set my motivation for thinking about this topic, I think it's pretty obvious that the next couple of decades are going to be golden age for observational black hole physics. So we're going to have sort of increasingly sensitive gravitational wave experiments. VLBI is only going to get better, and so we're really going to have a really beautiful window into the actual black holes up in the sky, the ones in our universe. And so I think it's really important, especially for theorists right now, to try to establish a point of contact between the sort of very impressive, but for most purposes, disparate developments in observational black hole physics and theoretical black hole physics. So, the EHT gave us our first real window onto horizon scale dynamics around supermassive black holes, and the astrophysicists are rightly interested in all of the what I would call sort of microscopic details of those systems. That means things like accretion flow, magnetic fields, sources of jets, all very interesting astrophysical phenomena. But people with my training in FTH and general relativity, I think, are more interested in what might be called the universal predictions for experiments like this, things which could be to some extent model dependent. Either they're fixed by symmetries or which might be able to forget about all of these microscopic details after some sort of suitable averaging procedure. Now, I don't think it's immediately obvious that there are observables of that kind. General relativity is certainly important for the dynamics around supermassive black holes, but it could have been that making quantitative predictions just always required you to know all of the detailed microscopic phenomena going on around the hole. And those details are extremely interesting, but they're also to some extent poorly understood. So, people like me would like to find some type of observable where the astrophysical effects all wash out. That's a little bit difficult for an experiment like the Event Horizon telescopes because the precise form of the black hole shadow really depends on the details of the accretion. So, to first order, you're basically taking a picture of an accretion disk, and so that will, of course, depend on what's actually going on outside the black hole. But, as these experiments improve the resolution, we're going to gradually become more sensitive to non-universal details of accretion and dynamics. But the thing that I want to discuss is this fact that already, sort of in the data that people in this building have gathered, there is a faint signal, which is already present in the image. It's not resolved now, but it probably will be in the future. And it's a pure general relativity fact. It's usually called the photon. So this ring is really just the optical image of nearly bound null geodesics. So the photons that appear at these points on the screen, they orbited the black hole many times before making it out to the asymptotic region and reaching the observer's telescope. And since the shape of that ring depends only on the mass and spin of the black hole and the angle of inclination for the observer, measuring that ring would provide very interesting mass and spin measurements for black holes, which is obviously a huge target for astrophysics. So that's sort of the background for why I'm interested in this subject. And I just want to do a brief pictorial review of what the photon ring is, and then I'll discuss its relationship to some other interesting gravitational observables. So we all know the Kerr metric. This metric is a little bit special because it has more symmetries than you would generically suspect an axisymmetric solution to Einstein's equations to have. And what that means for calculational purposes is just that the geodesic equation is completely integrable, which means you can write down a set of conserved quantities and completely describe motion just using those conserved quantities. So there's an energy, an angular momentum, something called the Carter constant, and that's enough to separate the geodesic equation and write down explicit solutions. So what that means is just that you can write down the completely general form of the tangent to a geodesic anywhere in the space-time, and only depends on the conserved quantities and the location in the space-time. The precise form really isn't important. There are just two interesting functions which are going to play a role in the discussion of the photon ring. The first is this radial potential, so that sort of controls the radial momentum of test particles moving around in Kerr. And this is just a quadratic polynomial in R. Okay, so the zeros of this quantity are basically turning points, geodesics in Kerr. They tell you sort of where the motion is bounded within the space-time. Similarly, this angular potential, big theta, basically tells you which angles about the black hole generic geodesic oscillates between. So you tell me the energy, angular momentum, and Carter constant of the geodesic, and then I tell you which cone about the equator this geodesic oscillates in between. Okay. So you probably know there's a couple of important astrophysical radii that go into the interpretation of black hole images. Obviously, probably the most important one is just the black hole horizon. And that's responsible for at least part of the brightness depression in the center of the image. There's also the set of bound null geodesics around the black hole. There's actually an entire band of radii, but the one which is closest to the horizon is equatorial, and it also interestingly follows the horizon of the black hole in the extremal limit and develops sort of an infinite proper separation from other interesting astrophysical radii in the extremal limit. And that's going to actually be important for some sort of peculiar features of images of near extremal black holes, and also properties of the quasi-normal spectrum of near extremal black holes, which I'll discuss a little bit later. Okay. And there's also the innermost stable circular orbit. Beyond that radius, circular orbits around the black hole become unstable, so that a small perturbation causes them to plunge directly into the black hole. So if you adopted sort of the simplest, most cartoonish model of a thin accretion disk, where you had matter just following circular geodesics, sort of adiabatically transferring closer and closer towards the black hole as the particles dissipated energy, then the inner edge of the disk would just be the ISCO, beyond which that stuff would plunge immediately into the black hole. Okay, so since part of the black hole image is just a weakly lensed picture of the accretion disk, the size of the ring really depends on the location of the inner edge and other details of the astrophysical system. Okay.
Sorry, that the
Yeah.
inner, you mean the inner edge of the disk?
Yeah.
Okay.
Yeah, so you have the talk, you said that like next generation experiments are going to measure more model dependent aspects, right?
Yeah, I think that's certainly the hope.
I see. But you're trying to look for model independent properties of photon ring?
Well, I think generically we're interested in both. I think people in our field are probably more interested in the model independent results, but you know, people in this field are certainly more interested.
And those are also going to get like more and more involved.
Well, I mean, there's, you know, proposals to build a much more expensive machine to image the photon. You can ask people in this room know much more about those proposals than I do. But yeah, I think it's probably going to happen and sooner than many other experimental results in FTH. So it's definitely something to keep an eye on. Any other questions? Okay. So, you know, given a model for an astrophysical black hole, how is it that we determine the resultant image on the observer screen? And there's basically two steps to this problem, which can be separated and solved sort of independently. So the first problem, which is purely a problem within general relativity, is just to solve for the geodesics connecting the matter sources in the black hole region to the observer screen, and determine the point on the screen hit by each geodesic. So that's a problem solved a long time ago, 1960s, 1970s. Second step, which is much more difficult, I would say, and of course much more model dependent, is to compute the photon intensities on the screen, basically by backwards ray tracing and doing radiative transfer. So you want to know basically for each of these geodesics that made its way out to the far observer's screen, how many photons did we load onto that geodesic in the system around the black hole? Okay, and then you also need to count for things like optical depth, because photons will also get absorbed when there's a lot of matter around the black hole. So again, in sort of the simplest model that you could make for a disk, which is just a thin disk in the equatorial plane, you roughly pick up a photon every time the geodesic crosses the equatorial plane. So that would be some sort of proxy for brightness on the screen, and more generally, the intensity will be related to the path length the geodesic has through the emission region. But that's really a problem for numerics. There's not much that you can do analytically, except for very special circumstances where you might have extra symmetry. Okay, so this is just the cartoon for the first part of the problem. It turns out that the point on the observer's screen that the geodesic reaches is completely determined by the energy, angular momentum, and Carter constant of the geodesic. So if you have some black hole that's emitting light in all kinds of different directions, if you know the energy, angular momentum, and Carter constant of the photon, then you know where it will show up on the observer screen. So these are relatively simple formulas that came from work in the 1970s. Now, the point is that the points on the screen that correspond to geodesics that spent more time in the emission region are going to appear brighter because they collect more photons. But in order to make a photon wrap many times around the black hole, you actually have to aim very carefully. So if we imagine sort of doing the reverse problem and sort of shooting photons from the observer screen towards the black hole, generically, if you shoot the photon, you know, towards the edges of the screen, nothing interesting is going to happen to it. It just passes through the space-time barely deflected. As you shoot photons closer and closer towards the black hole image, they'll start to be more strongly lensed. And eventually they'll start to wrap the black hole a couple of times. And the closer that you aim towards this so-called critical curve, the edge of the black hole shadow in some terminology, if you aim infinitely well, you can actually make the photon go around infinitely many times. Okay? And that's just the sort of optical reflection of the fact that the Kerr geometry contains a family of completely bound but unstable null geodesics. So those are, in today's terminology, usually called the photon ring. They're null geodesics with constant radius in Boyer-Lindquist coordinates. And for the Schwarzschild black hole, which is the one you might be more familiar with, there's just a single such radius at 3m. But for the Kerr black hole, there's actually a band of radii. So that single radius sort of opens out into a continuous family of bound null geodesics. And the sort of innermost and outermost bound null geodesics, they're equatorial, so they kind of behave like the Schwarzschild geodesic did. But for all of the radii in between, they actually explore a very complicated motion on the sphere around the black hole.
So for the definition of the photon ring, are you including, so there's the unstable bound null geodesics?
Mhm.
They cover not just the equatorial kind of rim, but they kind of oscillate in. The photon ring, would you consider all the unstable bound null geodesics in general, or just the ones that you are looking at on the equator?
Oh, no. So the two sort of extremal ones, they are equatorial, but
Yes.
everything else has complicated
Okay.
polar motion,
Yes.
and all of those are part
Are
of
part
the
of the
photon.
photon ring. Okay, thanks.
Any other questions? Okay.
May I have questions, please?
Hmm.
Can you hear me?
Yes.
Take the naked singularity case. Would we have trapped photon trajectories or not?
Yeah, I'm not sure. I have to admit I haven't thought about that. My guess would be that you do, because there's still just such a strong gravitational field. But I'm not really sure.
Okay, thanks.
Any other questions? Right. Okay. So an important property about these geodesics is that they are unstable. So the kind of very, pristine, finely tuned piece of the phase space, if you perturb them very slightly, then they will either plunge directly into the black hole or shoot off towards the asymptotic region where they can be captured by a telescope. And the critical curve, which is often really what observers mean by the photon ring, arises precisely from these photons traveling on such nearly bound geodesics. So obviously you will never see at your telescope a precisely bound null geodesic, because that spends all of its life around the black hole, but you can sort of make photons which go arbitrarily close to their bound radii and spend arbitrarily large amounts of time orbiting the black hole. And that's the thing which we're sort of interested in observing. Okay, so to understand to what extent these geodesics are unstable, and also to sort of develop some of the machinery for describing this mathematically, we want to consider sort of two separate geodesics which are very close to each other in phase space, but not identical. So one geodesic will be the exactly bound one, the one that is circling the black hole for eternity. And the other one is a null geodesic, which is just moved slightly off of its critical radius. So we perturb the geodesic by delta r, and we want to know how far these two geodesics become separated after some number of half orbits in the polar motion around the black hole. Okay. And that's going to be sort of a quantitative measure of the instability of these bound geodesics. Right. So the Kerr geodesic equation is separable. What that means is that you can basically integrate it. And one of the components of the geodesic equation relates a line integral on the radial motion of the geodesic to an integral in the polar direction for the geodesic. Okay. So this is not difficult to show since the geodesic equation is separable. The point is that the bound orbits, which we're interested in observing, they occur when you have double roots of this radial potential. Okay, so remember, a single root for the radial potential basically told you that there was a turning point in the radial motion. If you have two roots at the same point, it means that the geodesic can actually just get there and stop precisely. So double roots of this quantity are precisely the piece of the phase space associated to the photon ring. So if we just imagine doing that piece of the integral very close to the critical radius for the null geodesic, you'll generate basically a logarithm in the radial separation, right? Because we have 1 over the square root of the radial potential. We replace that with this quadratic approximation, so we get a logarithmic divergence in the integral, okay? And this is basically the signal of the instability, because the thing on the right-hand side of the geodesic equation, this angular integral, is just some known special function, some elliptic integral. So if we trace the motion of this geodesic over n half orbits in the polar directions, we'll have some fixed quantity which is proportional to a logarithm in the radial separation, which means actually that the radial separation is growing exponentially with the number of oscillations about the black hole. Okay, so this quantity gamma, which is basically a combination of the second derivative of the radial potential and this known angular integral, is usually called the Lyapunov exponent. It's a signal of instability in this part of the phase space. Are there any questions?
Are tilde, there is something defined in terms of.
Yeah, it's some complicated function in general, but the idea is that we're focusing on a specific geodesic, so we now know what the energy, angular momentum, and Carter constant of the geodesic are. That implicitly defines for us what critical bound radius this geodesic wants to spend most of its time on. And then we just perturb infinitesimally off of that radius and see how things grow as a function.
And it depends also on the parameters A and of your black hole.
Absolutely, yeah.
A question in the chat. Parth asks, if an upper bound on the effective potential of null geodesics are present, then null rays will be plunged into the singularity. While there's a photon sphere without an upper bound, then all null geodesics will be scattered. Sorry, it's not a question, it was a response, I guess, to the.
Sure, yeah, well, I can just draw a picture of what they're saying. I mean, the radial potential in the generic geodesics looks something like this. You basically can have, geodesics which come in, scatter off of the potential and fall back in. You can have ones that come from the outside, get shot back off. The ones that are sort of tuned right at the top of the potential and the bound ones, obviously, if you took this all the way up, then you would reflect basically everything. Okay. So the image of these nearly bound geodesics limits to a little pencil-thin curve on the observer screen as the number of these orbits around the black hole is taken to infinity. And that's what we usually call a critical curve of the black hole shadow. Now, because of this exponential instability for these set of geodesics, you have to actually aim exponentially well in order to make the photon go many times around the black hole. Okay, so if we imagine sitting at the observer screen, firing photons towards the black hole with variable energy, angular momentum, and Carter constant, which just means firing the photon from different points on the screen, then the point on the screen that you fire the photon from basically determines how many times that photon goes around the black hole before it shoots off to infinity or plunges through the horizon. Okay? So near the center of the black hole shadow, you're basically just exchanging direct light with the black hole. So you're shooting photons and they basically just plunge directly through the horizon. That's also why we get a brightness depression in the center of the image, because the interior of the horizon is causally disconnected from the telescope. Nothing is coming out of it. Okay, so in that circumstance, the number of windings is small. You're basically just shooting something which plunges directly in. Now, as you move radially outwards on the image, you get closer and closer to this critical curve. The photons that you're shooting at the black hole execute more and more windings around the horizon before they eventually fall in. And then you can imagine sort of passing through the critical curve on the image, and then the number of windings will start out very large, and it will gradually decrease as the photon moves away from the center of the black hole image, until eventually you're just sending and receiving undeflected light. Okay, so I think that's a little bit difficult to say in words. It's easier to say in pictures. So I'm going to go through a couple of very oversimplified models which have been in the literature for a long time. So the first kind of toy model for understanding how this works would just be to have a black hole sitting in the center of the universe, enclosed in a huge sphere which emits light uniformly. And we put the observer screen far from the black hole, but inside of this emitting sphere. So in that case, what will the image look like on the screen? Well, this is basically what I just described to you, but in pictures. So you get a brightness depression everywhere in the center of the image, where you're basically sending photons which eventually fall into the black hole. So if you're shooting photons from the screen towards the hole, these photons, no matter what complicated stuff they do, they eventually cross the horizon. They cross the horizon means that they do not exit to hit the emitting sphere very far away from the screen and observer, so you don't have any photons at that point in the screen. If we move that point around in the image, we move it closer and closer to this critical curve, the photons will start to do more complicated maneuvers around the black hole, but they'll all still eventually fall in. But the number of windings is increasing as we move towards the curve. Once you pass through it, you'll have photons which execute complicated motion around the hole, but eventually escape. They'll go off and hit this screen eventually, and that means that you will have loaded a photon onto that point on the screen, so the point appears bright. Okay, and then once you move farther away from the brightness depression, you're basically just sending and receiving direct light. So there's nothing really interesting going on. You're just loading photons from the screen onto the screen.
Okay.
Yeah.
Two questions. First, so what happens if you shoot something in between the innermost radius of the photon ring and the outside the horizon? Does it plunge in or does it?
Sorry, say it again. The innermost.
Like in between the photon ring and the horizon. You shoot something in that.
Generically, those will just fall into the.
They will. And second question, is there a reason why the black shadow on the screen is not perfectly like circular?
That's a reflection of two things. One of which is that I drew this for Kerr, which is only axisymmetric, and the second of which is that the image also depends on the inclination angle. So you sort of spontaneously break spherical symmetry by having a particular inclination to the black hole. So generically, for low spin, they are roughly spherical objects. When you either take them to be very extremal, so that they are nothing like Schwarzschild, then very funny deformations of the shadow can happen. Or if you're just not aligned well with the axis of symmetry, you can have.
Not a Schwarzschild with the normal.
If you just had Schwarzschild, any direction, obviously, that you look at it, well, oops.
The flatness, can you remind me, Dan, was when you had the spin right in one direction? And so the photons are like.
I'll have a slide about this.
Oh.
Yeah, this flatness, which I plotted sort of for effect, and here is a signal of high spin for black holes, and it only occurs for specific angular inclinations around extremal curve. But yeah, I'll discuss that explicitly.
Okay, chat question this time. Is there any unique relation between a photon sphere and an event horizon? Does the presence of a photon sphere explicitly hype the presence of an event horizon?
Well, I think generically, and I'm not sure to which extent these things have actually been proven. But I think to have sort of photon rings which do not lead to instabilities, one generally needs an event horizon. So, yeah, I mean, you could have worried about this set of null geodesics as a problem for the stability of Kerr, because what it really means is that it is possible to trap energy a finite way from the black hole. So you could imagine just pouring more and more energy into that region of the space-time and triggering an instability. That doesn't happen in Kerr, basically precisely because this double zero of the potential is a local maximum, which means that it's unstable trapping. So stuff which goes there can get trapped for a while, but it eventually wants to move away. If instead this potential developed a local minimum as well, which I think is what happens if you have this type of strong gravitational field but without a horizon, then you can have actually stable trapping, and that can become actually a problem for stability of the system. So I think there's some papers basically arguing that sort of for stable photon rings,
Excuse me,
sure, yeah.
are you able to take into account Hawking radiation?
This is a completely classical description. This part of the geometry is, of course, related to Hawking radiation. In fact, there's a cartoon for Hawking radiation in terms of sort of a thermal bath that exists between the horizon and the photon ring that sort of slowly leaks out to the far region. But nothing that I'm discussing here has anything to do with quantum mechanics.
Okay, thanks.
And so just to confirm like in the observer screen, the kind of like the black shadow is going to extend past the horizon into the photon, right? Like the first kind of like one dark piece of that is going to be at the photon ring and out. Or is there going to be like?
Yeah, so I mean, the photon ring is the region in phase space which neither falls into the black hole or escapes to the far region. So it's sort of a boundary in phase space. And you're kind of mapping the phase space onto this screen. So everything inside of this image is the pieces of phase space for which a photon that has one endpoint on the screen has the other endpoint on the black hole horizon. It doesn't matter how long it takes to get there, but it eventually crosses the horizon. Everything outside here corresponds to phase space for totally unbound null geodesics. So they can spend an arbitrarily long time around the black hole horizon, but they will eventually escape to the far region.
And that phase space separation and position space is being kind of cut at the radius.
Only for Schwarzschild. So for Kerr, the radius that you get caught up on depends on the energy, angular momentum, and Carter constant of the photon. So it's a geometric locus in Schwarzschild, but that's a very special case. In Kerr, it's a region in phase space, not a region in the geometry. So, yeah, these are all great questions. Any other ones? Okay, so second example, just to kind of demonstrate that the image can change depending on the light sources. We imagine basically the same setup, except for now, instead of putting the whole system in a big sphere that's emitting light, we just put an infinite planar sheet of light beyond the black hole, and we ask, what does the image look like? This, I claim, is the answer. This light piece right here is the critical curve. Now let's just kind of go through why this happens. So now, sort of the story which I told you before still holds if we start near the center of the image. So at that point, we're just exchanging light with the black hole horizon, which means that the photon has one endpoint on the screen, but the other one does not make it to the screen that emits light. So all of this is dark. Now, eventually, as you move towards the edge of the image, some of those photons will become unbound. So you'll pass through the point where they're always captured by the black hole, and they'll do crazy things, shoot off, and eventually some of them will reach this screen. Not all of them. There's actually a very intricate nested substructure there. But then when you move even farther away from the center of the image, some of these photons will be deflected enough, but not too much, so that they get bent basically 270 degrees. So they don't actually go into the black hole horizon, but they also get deflected so that they sort of become parallel with this screen, never make it to the screen, so you don't load photons there either. Okay, so then you have another sort of band of darkness where the photons have been deflected within a particular amount of angle, and then eventually you get outside of that range, and then you're again just basically exchanging direct light with the screen, and so the points look bright. Okay.
Dan?
Yeah.
On this, so this tells us that equatorial crossings will not strongly order the image of the image, because like the equatorial plane would be something that's parallel to the screen side. The number of times the photon crosses the equatorial plane is not really measuring the order of the image that you get in this scenario. Is that right?
The order of the image?
Yeah, like for example, you take a particular emitter in the bulk and take a particular observer on somewhere far out. You can look at the number of all the photons that connect these two. And if you order this discrete set by some segmentators, will that be, the question is, that will not likely be ordered by the number of equatorial plane crossings, right? Because of
No, yeah, I mean, the number of equatorial plane crossings is basically, you think of it sort of as a proxy for the path length near the photon, right? That's basically what it's doing. So for instance, if you had no emissions in the geometric support of the photon ring, then you wouldn't get any photons there at all, because there's just nothing to load onto those GPs. The assumption is that there is stuff emitting in that region to load photons on, and then we're going to use the path length as a proxy for how bright the point is. Any other questions?
The 270 degree ones, those don't come from the screen in some sense. The illuminated screen,
Yeah, that's why they look
they're-
dark, right? Yeah, it's something which hits this screen, but for instance, could have gone here and then come back out here. So it just never hit a light bulb to load on. It's not that interesting of a distinction. It's just there to kind of demonstrate that obviously the image does depend on what type of light sources that you have in the problem. And but of course,
very nice picture. I find it.
okay, yeah. So, for actual astrophysical black holes, neither of those idealized cartoons are relevant. The emission is all sort of right up close to the black hole, and the radiative transfer is much more complicated. You really just have to put it on the computer. And so the first, as far as I know, prediction for sort of a realistic image of a black hole came, I guess, more than 40 years ago by Luminet. This was supposed to be what a black hole would look like for a thin disk model with the edge-on observer. And that was, of course, experimentally verified by Matthew McConaughey during his interstellar trip to the black hole Gargantua. But for the rest of us, we all just have to rely on GRMHD simulations. We don't actually get to visit the black hole and see with our own eyes. And in GRMHD simulations, which many people in this building work very hard on, the thin photon ring does appear prominently to the naked eye. So if you just kind of glance at this thing, it's just pulled from one of the EHT image banks, your eye is drawn to sort of this bright thin ring around the black hole. You might not even be able to see these sort of wisps where actually most of the signal is. But unfortunately, as striking as it is, the photon ring really only counts for 10% or less of the flux in the image. And so, It's basically because this divergence in the path length is not really strong enough to really show up strongly if you're not sort of filtering for it. And so you can aim geodesics very close to this critical curve. They'll go around many times, but that either gets cut off by finite optical depth, or even if it doesn't, you have to aim so carefully that there's not enough phase space to produce a huge amount of signal on that critical curve. So it appears bright, but it actually produces little flux. And that's basically the problem that we encounter when looking for this object in the images. Okay? So instead, really, these images are dominated by the direct emission from the disk coming out to the telescope.
Yeah.
Yeah.
When you say the ring appears bright, but appears little flux, so how do you quantify that it appears bright?
Well, it appears bright to me. I don't know, like if you glanced at it, you would think, oh, that that must be the most important part of the signal. In fact,
So
people did, but it's not the case.
So it produces little flux, like relative to something.
Number of photons. Just think about the number of photons in this screen. And so we have a plot from this paper that we wrote many years ago. So if you think about this image, I'm going to cut out a piece of this simulation. And the people who do these simulations, they're able to track the photons throughout the GRMHD and the ray tracing. So they know if I have a photon here, what did it do close to the black hole? You can just count. And what you'll see is that in this band, most of the photons that you are getting are just sort of direct photons from the accretion disk. Okay, these sort of n equals to 0 photons, they're really pure astrophysics. You're just literally like taking a photo of something, right? Now you can see that as you move to photons which orbited the black hole, do at least 1/2 orbit, they start to concentrate closer to this critical curve, okay? And if they did 2 orbits, they're basically already sitting right on the curve. It just gets steeper and steeper, okay? So, but the bulk of the photons are sort of in this big fat band down here, right? And that's, you can't really even see it that well, but that's like this stuff right here. That makes sense? Yeah, so this is a plots from the Johnson et al. Paper from several years ago. I think it illustrates the point pretty well.
But then these n equals 0 photons are not plotted on this black images, right?
They are. They're like these ones here. There's sort of the wispy stuff.
So there's more of them, but they're like more distributed.
Yeah. Okay. Okay, so the photon ring unfortunately represents sort of a small fraction of the total signal. So it might have seemed that it was impossible to measure. You need longer baselines and higher frequencies for better angular resolution and more sensitivity to detect a faint signal. But all is not lost, because VLBI, it actually really filters stuff according to spatial wave number. You're measuring really the Fourier transform of the image. So it's not completely unrealistic that you would be able to pick up sort of very sharp features in the image, as long as there's not a lot of extra small scale power in the signal. Now, of course, there is lots of small scale stuff going on. Accretion disk is some crazy turbulent system, stuff going on at all scales. But you can hope that a lot of that will be transient, and that you might be able to average it out and pick out the piece related to the photon ring, which is sort of always sitting there emitting, sending photons to you. So that was part of the message in this paper from several years ago. There's obviously been a lot of work, follow-ups on that subject, proposals being made to put extra legs in space, and I think hopefully we will get to see this observable, certainly in our lifetimes. Okay, so yeah, the last thing that I want to say about the black hole shadows is this point that Maria was mentioning before. So if you were looking at a Kerr black hole and you are within 43 degrees of the equatorial plane, if that black hole is rapidly rotating, there's a very peculiar feature of the shadow, which is that it develops along straight edge on the left side of the image. So every photon that reaches the screen along or very close to this curve spent a lot of time at a particular radius around the black hole. What happens with these ones is that these photons actually spend most of their time very close to the horizon of the black hole. So the inner edge of the photon ring for Kerr in the extremal limit actually moves onto the horizon of the black hole. And the sort of vertical edge that we get here is actually sort of the optical prediction of this huge region that opens up right outside of the extremal black hole, which is usually called neck.
Can I ask, I don't know the answer, but if you have a spinning star that is also spinning, say, very fast, would something similar happen with the flatness? So is this a signal of the presence of the horizon? Maybe that's a more astronomy question. Black hole region.
Well, as we were mentioning earlier, I don't know that there's really the analog of a critical curve for a spinning star.
I have to find a star whose radius is inside, say, 3M, right?
Yeah,
Even in the non-spinning case.
like a neutron star.
Neutron star is not that small.
Okay.
Yeah, so we don't know such objects, but in principle, you can, there is a Bookdahl limit, which is inside the 3M.
Yeah.
So in principle, you can construct objects that live in that region. They will still have a photon ring. What will happen if you spin them up to critical? I have no idea.
Okay.
Yeah, that has not been studied.
I think you can, there's the regular black hole models. If you go beyond extremality, you actually get regular non-black hole objects.
Okay.
So they will escape the Bookdahl theorem because they are not perfect fluids.
Okay.
So they'll have isotropic pressure. These guys can have photon spheres, there is no, but when you define the critical limit, what do we mean? Because there's no horizons.
Yeah.
So we'll have to again approach the extremal black hole line from the regular compact target side.
Yeah.
So we'll probably get the same fluid.
That will be very interesting to study.
Yeah.
Yeah. You got all the metrics set. Yeah. That's right.
For next week.
Next week, yeah, right. Homework problem.
All right.
So Dan,
Mhm.
this vertical segment, you said you have to be in this region within 43 degrees.
Yeah.
So I guess above 43 degrees is just a smooth,
Yeah, this thing just
Rounded.
goes shorter and
Yeah.
then pinches on.
at 43 it is just forming and then it becomes longest at equator. And what can you say about the intensity of that vertical segment versus the rest?
Well,
of
I
it?
think, yeah, I think that depends on whether or not there's a bunch of stuff sort of right outside of the horizon of the extremal limit or not.
Yeah.
And if you met it, there's, divergent proper radial length right outside of the black hole in that limit, so there's room for lots of stuff. But you have to actually have a scenario where A, you've spun something up very close, and B, you had enough stuff to fill in that region to produce emission on that line.
It'll be interesting to see if the redshift, the gravitational redshift overpowers the.
Yeah, you're also finding
Yeah.
redshift. Great.
So that red region is exactly vertical?
Yeah, for an exactly extreme one. Okay, so the second kind of classical piece of physics controlled by the photon ring that I want to discuss in the remaining time is its relation to quasi-normal modes, which naively is a gravitational wave observable, not an observable for VLBI, but I want to sort of explain to you why there's a sense in which the EHT can actually measure sort of very high frequency gravitational waves. So if we imagine that we made a black hole through some violent process, there's really three time scales in the evolution of the system. So there's some merger phase, which is totally nonlinear general relativity problem and produces some prompt response, which scatters off to LIGO and depends to some extent on the details of the collision. That is just a problem for numerical relativity. Once the black hole has formed, then there's another phase. The system kind of settles down to equilibrium of quasi-normal ring. So this is sort of happening as the black hole is shedding its remaining hair that it acquired during the merger and kind of quieting down. This produces the exponentially damped ring down phase in the signal. And if we waited even longer times, the backscattering processes of the wave off of the long-range Coulomb potential around the black hole would produce polynomial price tails. So those won't be observable for a long time. It's also not really clear that they have much to do with the black hole. They have more to do with the long-range potential. So we're going to just set that aside. But the dynamics of the quasi-normal ring down phase is roughly linear. So we expect that the amplitudes are pretty small. We can approximate the evolution just by solving linear wave equations on the black hole background. And these quasi-normal modes, they're essentially the vibrational modes of the black hole. So the black hole is just curvature in space-time, but there's still some sense in which that object can vibrate in pure tones, and those are the things which we calculate with quasi-normal mode problem. They are damped oscillations because these are waves which sort of, though they were excited in the region around the black hole, they either fall through the horizon or dissipate off to infinity. Now, again, because of all of these special properties of the Kerr metric, it's possible to separate wave equations on the Kerr background and reduce it to a set of ordinary differential equations, but the ODEs usually cannot be solved exactly, and you really just have to resort to numerical methods to compute the spectrum. However, there's one exception to that statement, and that is that in the limit of large frequencies, so that we get to use the geometric optics approximation, quasi-normal mode spectrum actually becomes analytically tractable, and in fact, it connects cleanly with the geometry of the photon ring. Okay. So that's what I want to discuss for the last couple of minutes, and it's going to be an interesting statement because quasi-normal modes have an interesting interpretation in the holographic descriptions of black holes. All right. So in this perturbative phase, characterized by quasi-normal ringing, we're basically trying to solve a wave equation that looks like this. It's more complicated with gravitational perturbations, but a massless scalar field illustrates all of the basic ideas.
The ring down is everything once you don't have distinct horizons in some sense. Is that right? Once they've started.
Basically, I mean, it's a little bit hard to I would call it basically once linearized approximation is a good approximation. So yes, so you have some, slightly deformed horizon, nothing crazy is going on. All the really complicated merger stuff is roughly ended, and now you're sort of just regularizing the horizon by emitting waves. It's actually kind of a complicated problem for these people to make the distinction between merge and ring down. There's lots of arguments about whether or not they've actually observed quasi-normal modes. Okay, so we're basically trying to solve this relatively simple looking equation, and the way the physicists do it is just to study the problem mode by mode. So we basically use the symmetries of the problem to separate out the time dependence, angular dependence, and then the hard problem is really just solving the radial equation for these gravitational waves. So if you separate out using all the separation constants, you'll get an ordinary differential equation for the radial wave function. And it's a one-dimensional potential. And in general, there's not much more that you can say about it. You just have to try to solve that ODE on the computer.
So what does non-Hermitian boundary condition mean?
Exactly. So the type of solutions that we're looking for in this problem are ones that obey an ingoing boundary condition at the horizon, which means basically that we look for waves which do this on the left side of the potential, and outgoing boundary conditions of spatial infinity. Okay, so normally, if you remember about solving problems like this in undergraduate quantum mechanics, you would normally imagine you had some ingoing wave scatters into a transmitted piece and a reflected piece. The non-remission boundary condition basically means I ask that this be zero, or equivalently, I could imagine that I ask for a huge reflected coefficient that totally swamps the incident coefficient. Okay. So that's the idea. That's why these are resonances. They're sort of ingoing in one direction, outgoing in the other direction. And physically, that just means that, there's sort of nothing coming out of the past horizon of the black hole. It's just stuff which plunges in or scatters off to nothing. So if you impose those two boundary conditions on a second order ODE, you're going to get a discrete spectrum. And these solutions, they're interpreted as short-lived resonances with lifetimes which are roughly set by the temperature of the black hole up to order 1 numbers. Okay. So an important fact is that these solutions usually come in families, usually called overtones, and the higher overtones, they decay exponentially faster. So the non-Hermitian boundary condition means the spectrum that you get from this problem is complex. The imaginary parts tell you how fast these modes decay, and higher overtones decay faster because they have larger imaginary parts. Okay, so I'm not going to go through all of the formalism to solve this problem with geometric optics, but basically what happens when you try to solve this problem is that the real and imaginary parts of these quasi-normal modes, they become related to geometric quantities of the photon. So the real parts will end up getting controlled by orbital frequencies of the null geodesics around the black holes. And the imaginary parts get set by these Lyapunov exponents, which were a signal of the instability of the geodesics, and instability means things will tend to decay, and that's why they show up in the imaginary part.
Dan, I have a question. If you want, I can do it.
No, go ahead.
So, where is the surface gravity is, or what is the temperature of the black hole is? Is it in the?
It's usually in this piece right here. So, for instance, if you took the BTZ black hole, which is sort of the simplest black hole which we know, which we can solve everything exactly, then this factor is like 2 pi times the temperature of the black hole.
This is very interesting because the Lyapunov experiment is telling you about the radial simulated photon shell.
Yeah, there's a sense in which it's kind of like some type of local temperature for excitations off of the horizon. That's never been made.
But it's not the horizon, right?
This is the photon.
This is all in the photon shell.
That's what I'm saying, off of the.
Yeah.
So
Oh, but quite a long way.
the temperature people usually think of as being associated to the horizon. This is kind of in some sense, a temperature which controls decay, but for stuff not right on the horizon. Okay, so just to remind you briefly how this works, and I'll be quick, I don't want to go over. So when we take the short wave limit of a wave equation, we're basically trying to approximate the solution in terms of some rapidly varying phase and some amplitude, which we ask to not vary as rapidly as the phase does. Okay, and if we just take this ansatz and plug it into the wave equation, it has a pretty simple form in terms of the gradient of this phase function. And so I'll call the gradient of SP. You get basically algebraic things in P and differential operators in P. Okay, so at this point, nothing has changed. I've just plugged in an ansatz, but now geometric optics means that I'm going to try to solve this equation approximately order by order in P.
Chat question. Why do we consider the imaginary part of the frequency of quasi-normal modes of ingoing and outgoing plane waves? Is there any physical relevance?
Yeah, it is understood sort of as the time scale for decay of that particular mode. So I mean, it's the same problem if you think about quantum mechanics, sort of with a tunneling potential. You can sort of set up a non-Hermitian ODE for that system, and the real part tells you sort of the kind of approximation to the actual energy of that resonant state, and then the imaginary part kind of tells you the width of that state. So sort of the spread energies, because that mode is not absolutely stable. Okay, so if we just try to solve this order by order, the first term just says that P should be a null vector, and it turns out that because P is a gradient, it will also solve the geodesic equation. Okay, so to solve the first piece of geometric optics, this tells us that we actually need to work with a null geodesic in this space-time. But then we need to discuss the boundary conditions for this solution to the wave equation. Because we are looking for solutions with a peculiar boundary condition that's ingoing at the horizon, outgoing at spatial infinity, what you actually need is a geodesic with a double zero in the radial potential. Okay, so it turns out that in order for solutions to this equation to obey the quasi-normal boundary conditions, you need to be working with a geodesic, which is a double zero of the radial potential, and that precisely defines the photon. Okay. So the subleading term in the geometric optics expansion relates the expansion of that congruence of null geodesics, the covariant derivative of the tangent of the geodesic, to the derivative of the wave amplitude along the geodesic. So transport the amplitude along the geodesic as controlled by the expansion of that congruence of geodesics. So in particular, if that expansion is positive and the wave and the geodesics are kind of dispersing, then what you'll find is that this amplitude is exponentially decaying along the congruence. Okay, so positive expansion, this unstable property of the null geodesics, leads to exponential
That's
decay.
related to the optima.
Yes, it will be. Okay, so the summary is just trying to solve the wave equation with this funny boundary condition that tells you that you need to work with a null congruence whose tangent is on the photon ring, and the expansion controls the decay of the amplitude. And it turns out, as Peter just mentioned, that this expansion is actually related to the Lyapunov exponent of the associated geodesic. Okay. So that's sort of the order one piece that tells you the first quasi-normal mode. What about the overtones? Well, you know, if you think about it, if we're trying to solve this equation here, any quantity which is annihilated by this operator, in other words, which is parallel transported along the geodesic, will give you another solution to this equation, because I can commute it past this thing, and then I can just multiply by this thing, and that'll define a new amplitude which solves this equation. Okay, so if we manage to find functions which are constant on these congruences of geodesics, then we can actually generate families of solutions to this wave equation just by multiplying the seed solution by this function to some power n. Okay, but of course we know that this quantity e to the minus gamma t delta r is constant along these nearly bound null geodesics, because I already told you that delta r grows exponentially like e to the gamma t. Okay, so this thing is sort of trivially constant along this bound or nearly bound null geodesic, which means, okay, you can't see that, but which means that if we had some initial solution, which is like e to the minus gamma half t e to the is, we can generate a whole overtone family by multiplying by e to the minus gamma n times delta r to the n. Okay, and that turns out to be precisely the form of higher overtone wave functions in the near peak region. So that form has been known for a while, but this is kind of an interesting geometric way, in a more covariant way, to understand it. So I'm going to skip a bunch of stuff and just go to the conclusions. I just want to say, that there's one way you could have produced solutions to that equation was be if you had a killing symmetry, because then you would obviously have a conserved quantity along every geodesic, and that would allow you to generate solutions in this form. And this other way, generically, is nonlinear in the momenta, so it's not coming from a killing symmetry, but you can really run this procedure for any black hole. You just need to get control over the behavior of the solution in the near ring region, and then you can build entire families. So there's some, some interesting hints of enhanced conformal symmetry in this problem. I'll maybe save that if people have questions, and I'll just wrap up by mentioning the relation of this problem to the quantum mechanics of the Kerr black hole. So there's kind of this paradigm in At TH, where we understand the e to the s Bekenstein-Hawking entropy as roughly a state count of approximately thermal high energy states in a quantum mechanical system, which is supposed to describe black holes. Okay. And this dictionary has been made excruciatingly precise in anti-de Sitter space. It's still not really understood very well for black holes in asymptotically flat space, but we can sort of follow our nose using intuition from ADS and try to understand the analogs for Kerr black holes. So in this dictionary, you can imagine perturbing the black hole, meaning that you perturb the quantum mechanical system. And in that case, the response of the black hole is just described by linear response theory in quantum mechanics. And the dictionary by which we understand the Bekenstein-Hawking entropy maps the quasi-normal ringing of the black hole to these damped oscillations of a perturbed thermal state as it relaxes towards equilibrium. So if you imagine you have some correlation function which depends on time, that's the quantity which you use to compute linear response. Its behavior as a function of time is controlled by these frequencies, sometimes called the Ruel frequencies. And ADS-CFT basically tells you that those frequencies are precisely the quasi-normal mode frequencies. So we don't have a proof that that's also true for the Kerr black hole, but we suspect that it's true. And the point is just that, for Kerr, we have a good analytic formula for many of those frequencies, in particular for the shortwave piece of the spectrum. The dispersion relation is quite complicated, and actually no proposed dual to the Kerr black hole accounts for it. So that's kind of a target for HepTH, is to just find some quantum mechanical system whose shortwave Ruel spectrum has this behavior. It hasn't been done, with one small exception, which is that, so here in these plots, I plotted basically the dispersion relation for these quasi-normal modes for various spins of the Kerr black hole. And you can see that something very interesting happens at very high spin for waves with a particular amount of angular momentum. Basically, the dispersion relation becomes linear and the imaginary parts go to zero. And this is basically the spectral signature of the throat opening up in the extremal limit, because this type of dispersion relation here is a signature of explicitly realized SL2R symmetry. And these imaginary parts, which are going to zero linearly in the temperature, they're precisely the formula that you would have in BTZ. So that the imaginary part is like 2 pi IT n plus a half. Okay. So this part we roughly understand through Kerr CFT. The rest of the spectrum, we really don't know any quantum mechanical system that does that. But if we believe that Kerr is actually described by some quantum mechanical system, then it is going to be constrained actually by these type of classical universal features of black hole physics. So we could sort of think of this photon ring as emergent geometrization of the high frequency Ruel spectrum in the dual quantum mechanics. That gives us a couple of puzzles, sort of why should this part of the spectrum be universal in quantum mechanics? Ordinarily low frequency stuff is universal. Here we assumed to have a prediction for high frequency universality. I'll skip these and just leave the conclusions here. So that the photon ring controls many distinctive classical features of black hole physics, some of which can be measured by the event horizon telescope and its extensions, some of which relate to gravitational wave physics. And the ones that relate to gravitational wave physics actually have a pretty interesting interpretation in holographic descriptions of black holes. So I'll end there if there are any questions.
You could sort of see it in either direction. You could say, start with the classical and the constraints of the quantum mechanical. Or you could say, start with the quantum mechanical and the classical is inversion.
Yes, and in ADS-CFT, we can really take either approach. Unfortunately, for black holes in flat space, we really don't have the top-down constructions. So it's more of a bottom-up, try and see how many things we can say about the quantum mechanics and constrain it. it's not as if we understand every black hole in ADS. We understand with a lot of detail, particular ones that come from particular UV completions of Einstein's general relativity. But it's entirely possible that we will never actually have the complete UV completion of gravity in our universe, in which case it's less interesting to know the exact quantum mechanical system that describes the black hole. Rather, you would like to be able to understand sort of its universal features and understand sort of how those reproduce the sort of semi-classical universal features of the black hole. But yes, it's certainly, and that's kind of the second point that I had. You could imagine if you did know the quantum system exactly, you would view the photon ring as sort of an emergent structure that was encoding universal properties of that one.
So in the, it was very interesting to see the dispersion relation that you had. So typically the version I've seen is that frequency is the inverse of the critical curve radius, at least in spherical symmetry. That piece. So it's 1 over shadow size or whatever.
That's for Schwarzschild. So for Schwarzschild, this is like 1 over 3 root 3 L. But this is also 1 over 3.
Exactly.
They're different.
So what I was trying to understand is in Schwarzschild, how do I see this mu dependence? Is the 1 over 3 root 3 happening for n equal to L modes, or
For Schwarzschild, there's a huge degeneracy in this spectrum. There's for every fixed L, so this L is like the spherical harmonic L, you have a huge degeneracy. And because we're at large L, there's a huge number of states, all with the same frequency. When you turn on rotation, you basically split the spectrum. And at small frequencies, you can sort of imagine treating it in perturbation theory, but at small spins, but at large spin, it's just a completely different problem. And it just has nonlinear behavior, which is very striking for a particular part of the spectrum and basically unexplained for the rest of the
And what is the function of the order of mu?
yeah, it's like the energy of the orbit divided by L in a particular scale. So it's related to the actual solution of the geodesic equation. And this is just related to the Lyapunov exponent divided by sort of the orbital period of the geodesic.
But this, like this line at the end, this SL2R kind of like spectrum, and this is only for near extremal in a precise range, right?
Yeah, so this is for a near extremal black hole in the geometric optics limit. And what this says basically is that there's a bunch of quasi-normal modes, which basically can bounce around for as long as they want in the extremal throat because it's so long. So if you kind of imagine blowing out the near horizon region, these are just the linear solutions to the wave equation that you're familiar with for finite temperature black hole and ADS3 like geometry.
Is there like an obvious intuitive explanation why the critical kind of like parameter that controls when this SL2R behavior emerges is this mu?
Yes, because it's precisely the geodesics with this value of mu that belong to the part of the photon ring that moves into the throat. So the rest of these geodesics, they sort of belong to the part of the photon ring, which stays a couple of Schwarzschild radii away from the horizon in the extremal limit. The ones with these values of mu are on the part of the photon ring, which is moving on to the event horizon in the extremal limit. And that's why they kind of explore the neck region, and that's why they have a much simpler dispersion.
these are all the prograde ones?
Yeah, they all rotate. You have to rotate with the horizon. This is just the angular velocity of the horizon. It's like 1 over 2. It's just the super radiant.
Last one then. There are these second order quasi-normal modes so you're analyzing the first linearized, ring down. There are the non-linear quasi-normal modes. So they're like the second. Do we know anything for PTC in that case?
Actually, I'm totally unfamiliar with that subject. I know what you're talking about, but I haven't thought about it. But yeah, I mean, PTZ might be an interesting place to be.
Thanks.
Okay, Thanks, Dan.